When you think about a blockchain, every single transaction, where does it go? Well, it gets stored forever. And that creates this massive data problem that just keeps growing. But what if there was a way for a blockchain to securely forget? Today, we're diving into something called MuHash. It's kind of like cryptographic magic, and it might just be the solution to one of blockchain's biggest headaches. All right, let's really get into this. Back in 2009, when Bitcoin was brand new, its entire ledger was tiny. I mean, super easy for anyone to download and store. But fast forward to today, whoa, it's a completely different story. The ledger has just ballooned into hundreds and hundreds of gigabytes. It's this massive overflowing archive that just never stops growing. And that relentless growth, well, that's a huge problem. It creates a massive barrier for regular people who want to run a full node. And running a full node is absolutely essential for decentralization. So it makes you wonder, right? What if a blockchain didn't have to remember everything? What if it could securely forget? Okay, so before we can really get into the solution, we've got to understand the problem itself. So first up, let's talk about the blockchain storage problem and why these digital ledgers just keep getting bigger and bigger. So here's the deal. The security model for something like Bitcoin is basically built on total recall. To be a full, trusted participant on the network, you have to download and store every single transaction from every block, all the way back to the very first one. It's this unbroken chain of data that you can never trim. Now, that model is incredibly secure, for sure, but it's just not sustainable if you want to scale up to, a global level. But what if there was a smarter way to keep the books? And that brings us right to our next topic, MuHash, which is basically a much smarter ledger. So what in the world is MuHash? Well, it stands for multiplicative hash. And its key feature, and trust me, this is the really revolutionary part, is that it creates a single, secure digital fingerprint for a whole set of data. But it lets you add or even remove things from that set without having to recalculate the entire thing from scratch. That's a game changer. Yeah, this ability to do incremental updates is basically its superpower. It's also order independent, which is a fancy way of saying it doesn't matter what order you add or remove things in. That final digital fingerprint will always come out the same. Pretty cool, right? And on top of all that, it's super secure and really efficient. That collision resistance thing just means it's pretty much impossible for two different sets of data to accidentally create the same fingerprint. It's just perfectly designed for data that's always changing. Okay, I know. This sounds great in theory, but how does it actually do that? How does it perform this magic of adding and subtracting from a hash? Well, believe it or not, the math behind it is surprisingly simple and kind of elegant. Let's break it down. So to get the core concept, just forget about complex algorithms for a second. I want you to just picture two simple running tallies. That's it. The first one, we'll call it the numerator, keeps a running total of everything you've added to the set. And the second one, the denominator, keeps a totally separate tally of everything you've removed. And here's how it works. It's so simple. When you want to add something, you just multiply it into that added tally, the numerator. When you want to take something away, you multiply that same item into the removed tally, the denominator. And then, to get the final hash, that fingerprint that shows the current state of all your data, you just divide the added tally by the removed tally. Seriously, it's that straightforward. Okay, now you might be thinking, wait a minute, if you just keep multiplying things, won't those numbers get astronomically huge? And that's a great question. That's where this really clever safety net comes in called the modular prime constraint. Just think of it like a mathematical boundary. It makes sure that the numbers in our two tallies never spiral out of control, keeping all the calculations totally manageable and super fast. All right, so this isn't just some cool theory stuck in a white paper. Nope. This is being used right now in the real world to solve that exact storage problem we were talking about. So let's check out a real-world example. We're going to look at Kaspa's pruning in action. And what's really interesting here is that the whole idea of pruning, cleaning up old spent transactions, it's not new at all. Bitcoin's creator, Satoshi Nakamoto, actually talked about it way back in the day. So the problem was never the idea. The real challenge was always how. How do you actually do it without messing up the security of the whole system? And this right here is the aha moment. This is what it's all about. You've got the old model on one side, store every single transaction forever. And then you've got Kaspa's model on the other side. By using MuHash, it only needs to keep track of the unspent funds, the UTXOs. It can securely prove the entire history of the blockchain without actually having to store all of it. That's huge. So how does this actually work in practice? Well, Caspa cleverly separates two different types of data. First, you have the really critical stuff, the consensus data. These are the block headers that contain that final MuHash value. That stuff is kept forever as the ultimate proof. But then you have all the bulky application data, the actual details of old spent transactions. That can be safely removed or pruned. And the result? A blockchain that stays dramatically smaller and way more efficient as it grows. So we've seen what MuHash is and how a project like Caspa is putting it to work. But let's zoom out for a second. Why does this really truly matter? Because this is about so much more than just saving some disk space. This is about the entire future of blockchain scalability. Because think about it, when you solve this data bloat problem, you unlock a ton of potential. You're not just making the blockchain smaller, you're actually laying the foundation for a network that can be faster, more accessible for everyday people to use, and way more decentralized, even as it scales to millions of users. Let's just break down the impact here. First, you get efficiency. That means it's cheaper and easier to run a node. And what does that lead to? More decentralization. Because you're lowering the barrier to entry, more people can actually participate in securing the network. And when you put those two things together, that's what enables real long-term scalability. It allows a network to grow to a global scale without collapsing under its own weight. So that leaves us with a final, really powerful question to think about. We've just seen how a clever piece of math can let a network remember exactly what's important and securely forget everything that isn't. So, could this kind of smart, efficient pruning be the real key that finally unlocks a truly scalable blockchain future for all of us? It's a pretty compelling thought, isn't it?